In this example, we have that in oceanography, the concept of longshore transport refers to the movement of particles of sediment by the effects of waves on a shoreline. When the waves wash up onto a beach, they do so at an angle, but when the same water washes back down the beach, it moves straight down the slope of the beach. The upward moving water, known as the swash, pushes sediment particles along the beach, while the downward moving water, the backwash, brings them straight back. With every wave that washes up and then down the beach, particles of sediment are moved along the beach in a zigzag pattern. So we have here that let's say the particle begins at point A in the diagram, down here, and follows the pattern indicated by the swash and backwash, meaning that the particle is following the dotted line towards the shore of the beach, and then back down with the backwash back down the slope of the beach. And it keeps following this pattern over and over and over again. That is longshore transport. If the slope of the beach, the vertical backwash, is 18 feet, and the waves hit at the beach at a 40-degree angle, we're going to find what is the total horizontal distance traveled from the point A to point B. So that means that we have the vertical backwash, that's a vertical line here, that is 18 feet. That's going to be 18 feet in each of these triangles. We also have that the waves hit the beach at a 40-degree angle. If they're hitting the beach at this 40-degree angle, that also means that the angle measure inside of each of these right triangles on the beach is 40 degrees. What we are trying to find here then is the distance from point A to point B. Since this is a constantly repeating pattern, all we really need to find is one of these side lengths for one of these right triangles, and then multiply that by 4 in order to get our full distance. So, if I move this down so I have a bit more room, we are really working with a right triangle here with a 40-degree acute angle measure, a side of 18 feet that is across or opposite of it, and we are trying to solve for the side length x. In this case, since we have a degree measure and a side length, and we're trying to find another side length, we should be using one of the 3 basic trig functions. We would not use sine because sine is opposite over hypotenuse. We do have the opposite, but we are not trying to solve for the hypotenuse, nor do we need it. We would not use cosine because that is adjacent over hypotenuse. We are trying to find the adjacent, but again, we do not have nor need the hypotenuse side. The most appropriate trig function to use in this circumstance would be tangent. Tangent of theta would be defined as the opposite over the adjacent. This is the most appropriate one to use because relative to our angle measure, 40 degrees, we have the side opposite of it, and we are trying to find the side adjacent to it. Therefore, I would write this as tangent of 40 degrees is equal to the opposite of 18 divided by the adjacent of x. To solve for x, we would multiply both sides by x, and then divide both sides by tangent of 40 degrees, which results in x equals 18 divided by tangent of 40 degrees. Now that we would need to approximate using a calculator. So make sure that you are in the appropriate mode here. We are in degree mode. And then we would solve this as 18 divided by tangent of 40 degrees. That gives us approximately 21.45, which would also be in feet. This is not my final answer because this is simply the adjacent side of one of the 4 triangles representing the distance from point A to point B. If I do want to find the full distance from point A to point B, we would take this value and multiply it by 4. We will take 21.45 and multiply that by 4. Or I'll use the more correct value of 21.45 with the remaining digits after that. So 21.45156. I'll multiply that whole thing by 4. If I round this to the nearest hundredth of a foot, I have that this particle has moved 85.81 feet. And that would be my final answer to this problem.